Hello everyone. Today we will be beginning our discussion of scheduling problems. Now, scheduling problems are always going to have four basic elements. So those four elements are the processors, the tasks, the processing times, and the precedence relations. So we'll go ahead and talk about each of these four things in order. So the first one of these things, the processors, basically is just whoever or whatever is doing the work for whatever project we're working on. So scheduling problems can represent all kinds of things, anywhere from construction work to cooking, maybe class projects. Any of these things can be represented by scheduling problems. And the idea is that our processors can be either people, machines, computers, whatever, that are doing the work. So say you have a class project and there's 3 people working on it, we would say that we have 3 processors for that. The next element is the tasks, and the tasks are basically just indivisible units of work that the project is comprised of. So say you have a project that you're working on and there's 5 different things that need to be done as components of that project, we would say that we have 5 different tasks that are part of that project. Now, when we are in the process of working on a project, a task can have any of 4 statuses, which I have listed here. So the first one is ineligible. This means basically we can't start working on that task yet because there's some other task that needs to be done before we can start working on it. The next one is ready. That means basically that we've got all of the prereq tasks done. We can start working on that whatever task we're looking at, but we haven't started on it yet. In execution means that we have started on that task but not finished it, and then finally completed means that we have finished that task. The next element is the processing times, and the way that we represent these processing times is with the numbers in parentheses next to whatever abbreviations we're using for the task. So I have a couple of example schedules right here on the board. So if we look at this top one, if we have A and then 2 in parentheses, that means that we have task A and it takes 2 hours or 2 minutes or 2 days or whatever our unit of time is to complete. Or B would be 1 hour or whatever unit we're using, C3, D3, and so forth and so on. Now, when we are figuring out processing times, we are using 3 simplifying assumptions that we're operating with, basically. So the first one of these is versatility. And what that basically means is that any processor can complete any task. Next, we have uniformity. This is saying that basically, no matter which processor we assign any given task to, it's going to take the same amount of time to complete. And then finally, we have persistence, which basically means that once a processor has started on a task, it's going to be uninterrupted until it completes that task. Now, realistically, when we're dealing with projects that are being worked on by people, probably none of these 3 are really totally accurate assumptions. But for the purposes of figuring out these scheduling problems that we'll be looking at, these are the assumptions that we will be using. The last element of scheduling problems is what we call the precedence relations. And the precedence relations basically just say which tasks have to be completed before whatever other tasks. So an example would be something like this, where we have A that precedes B, which precedes C. So this would mean before we complete task C, we have to complete task B. Before we complete task B, we have to complete task A. If we have something like this where A precedes B and B precedes C, it follows from this that A precedes C. In other words, because B, you have to have A done before B and B before C, you have to also have A done before you can do C. One thing that we cannot do with precedence relations is have a cycle. So this would be something like what I have drawn here, where A precedes B, which precedes C, which precedes A. We've got this little loop thing going on here. we can't have this because this would basically make it impossible to do any of these tasks. We can't do A, or we can't start with A because we have to have C done first, but we can't do C until we have B done, but we can't do B until we have A done, but we can't do A until we have C done, and it just keeps going endlessly. So this is why we cannot have a cycle like this with our precedence relations. Now, when we are making schedules, such as these examples that we have drawn here, we have something that we call the finishing time, and that's basically the total time that it takes to complete the entire project. Now, we abbreviate this fin, and we use the abbreviation opt for the optimal finishing time, which is basically the lowest possible finishing time that we can have for the project. So I have examples of two different schedules for the same project up here. Notice this top one has no idle time versus this bottom one, P2 is idle for 2 hours or whatever time unit it is that we're dealing with. And our finishing time is 7 versus 6. So this would be an example of a non-optimal schedule versus an optimal schedule for this project. And ideally, whenever we are making an optimal schedule, we want to minimize the idle time for our processors in that schedule. Thank you for watching, and as always, I'm happy to help with any questions you have.